everyone. In today's session, we're going to go through some basic acid and base theories. And by now, you should already be very familiar with the terms electron cloud or electron orbitals because I'm going to use them quite extensively in today's session. So I'll be going through the Bronsted-Lowry acid and base theory as well as the Lewis acid and base theory. So here is a brief summary of the contents. And without further ado, let's dive straight into the BL theory. So the BL theory is based on the transfer of H class from the acid to the base. So the acid is the H class donor, while the base is the H class acceptor. And a term that we are going to use is the conjugate acid-base pair. So these are the acid and base that differ by one H class. So what do I mean by that? For example, we can consider the reaction between water and ammonia. When water reacts with ammonia, water is acting as the acid, while ammonia is acting as the base. So after the water protonate or transfers the H plus to the ammonia, the water becomes hydroxide and the ammonia becomes ammonium ion. So in this case, the conjugate acid, we have two pairs of conjugate acid and bases here. So the first pair is water and hydroxide. So water and hydroxide is a conjugate acid and base pair where water is the acid and hydroxide ions is the conjugate base, while ammonium and ammonia is your other conjugate acid base pair where ammonia is the conjugate base and the ammonium ions is the conjugate acid. So when you take a look at a reverse reaction, so the reaction goes from right to the left, then here the hydroxide is base while the ammonium ion is the acid. So you realize that when the reaction goes the reverse way, you kind of swap. So the conjugate base becomes the base and the conjugate acid becomes the acid. So let me repeat that again. When you have water and ammonia reacting together, your water becomes hydroxide and water is a conjugate acid while hydroxide is the base of that acid. And for ammonia, ammonia and ammonium ions is another conjugate acid and base pair. So you call these pairs conjugate acid and conjugate base. And there are some common types of Bl acids that you should take note of. The first is dissolved hydrogen halide. So for example, you have your hydrochloric acid, HBr, and then you have your oxo acid. So those are your nonmetals with double O or single bond O, single bond H bonds. So oxo acids are your sulfuric acids and a lot of other acids where you see the anion has a nonmetal attached to several oxygens, and the oxygen will sometimes be double bonded to that non-metal ion and sometimes single bonded to the non-metal ion and single bond to hydrogen. And this OH bond might break to dissociate the H plus ions. And the third type is your aqua ions. So those are your metal cations with water ligands. So the reason aqua ions are considered acidic is because the charge of the metal cations will distort the electron cloud of water, which weakens the OH bond in water, H2O, and causes the H plus to be released more easily. So an example is your iron 3 plus ion, and it's surrounded by 6 water molecules. So we call these water molecules ligands because the lone pair on the oxygen actually kind of dative bonds to the iron center, and because of this, the electron actually gets pulled towards the iron center, and then the OH bond in these 6 water molecules will be weakened. And that's why you can break that OH bond more easily, and the acidity of the solution increases. So if you dip a blue litmus paper inside a solution of iron 3, then it will actually turn red because solution is acidic. Then the last common type of Bl acids is, of course, the carboxylic acids, which are organic acids, and they contain the COOH group. So the OH bond is also quite is can also be broken, and then the H plus can be released. So another term I want to cover here is polyprotic acid. So polyprotic acids can donate multiple H plus ions successively. So for example, sulfuric acid. So here, unlike what might be taught at secondary school level, the H plus, the two H plus ions in a molecule of H2SO4 actually do not fall off at the same time. Instead, after you dissolve some H2SO4 in water, the first H plus ion might dissociate first, and then you have your HSO4 minus ion, and then another H plus ion might dissociate from that to form SO4 2 minus ions. And of course, these two are just reversible reactions and have their own equilibrium constants. And that's something we're going to cover later on. So there are several things we can do when we compare acid strengths. For example, we compare the acid dissociation constants, we compare the stability of conjugate bases, and we compare the charge density. However, usually in Olympiad questions, not all three pieces of information will be available to us, and therefore we have to extract our own pieces of information and make deductions from there. So let's talk about acid dissociation constants first. So acid dissociation constant, or Ka, is just the equilibrium constant for this reaction. So it's equals to the concentration of the H plus ions times the concentration of the A minus ions over the concentration of the undissociated species inside a solution at equilibrium. So here, pKa is something that we often use to represent how strong the acid is, because sometimes Ka by itself can be quite small. So for example, 10 to the power of -5 and so on. And we don't want to keep writing the number over and over again. So we use something called pKa, which is basically you put that on a log scale. So when you write P in front of a quantity in chemistry, it just means negative log base 10 of that value. So pKa is just negative log 10 Ka. By doing this, by comparing the pKa's instead of just comparing the Ka's directly, we can actually represent the numbers in an easier manner. So a smaller pKa or a greater Ka indicates that the thing is a stronger acid. So for example, when you compare, let's say, ethanoic acid with, let's say, hydrochloric acid, then the hydrochloric acid would have a smaller pKa. In fact, the pKa is negative compared to ethanoic acid, and that's how you know HCl is actually a stronger acid. So here, why is this the case? So a larger Ka basically means that the H plus times A minus concentration term here is greater when you compare two different acids, and this term here, the HA term, is smaller. And because of this, we know that the position of the equilibrium actually lies more towards the right. And because of that, the acid dissociates more fully and more completely. And that's why a larger Ka means the acid dissociates better, dissociates more. And that's why it's a stronger acid. And by having a larger Ka, it actually implies a smaller pKa. So because you take the negative log 10 of Ka, so larger Ka gives you a smaller pKa. So smaller pKa also indicates a stronger acid. Okay. Moving on, another way that we can compare the strength of acids is to compare the stability of conjugate bases. So we often do this when pKa or Ka values are not immediately available to us. So There are several trends that we can observe across the periodic table. So across a period, the electronegativity of the element increases, and the respective element will be more stable to bear the negative charge. So after you deprotonate an acid, or after the acid transfers, gives away a H plus ion, it might need to bear a negative charge. So the anion that bears the negative charge, if the element that bears the negative charge is more electronegative, then it will be more stable to bear the negative charge. So then the stability of the conjugate base will increase because the element is more stable to bear the negative charge. So the stability of fluoride ions is greater than hydroxide. So F has a greater electronegativity than O, which in turn has a greater electronegativity than N and C. So here F will be the most stable to bear the negative charge. And here you need to take note which atom or which element the negative charge is located on. So here, although we write hydroxide like this, the negative charge is on the O atom, and here it's on the N atom, and here it's on the C atom. So we take a look at an element or atom where the negative charge is located at. So here, of course, F is the most stable, F minus is most stable, and yeah, so it's the stability increases across a period. And because this, the acid strength of HF is greater than water, greater than ammonia, and then greater than CH4. So this is because the conjugate base becomes more stable. So why does an increase in stability of the conjugate base mean that the acid strength increases as well? Well, because when the conjugate base becomes more stable, so when the conjugate base becomes more stable, the the position of the equilibrium actually lies more towards the right, and that means the conjugate base is formed more favorably compared to when the thing stays undissociated as an acid. And so because of this, when the stability of the conjugate base increases, the degree of dissociation of the acid actually increases, and that's why the acid strength will increase across a period. Um, another way to Another thing we need to take note of is that you should because when the stability of the conjugate base increases, that actually means the strength of the conjugate base decreases. So what do I mean by that? So for example, we know that in most cases, hydroxide would be a stronger base than fluoride because hydroxide is less stable than fluoride. So it is more likely to grab the H plus ion. So it is more likely to grab a H plus ion and form back water. Then compared to when F minus grab a H plus ion to form back your HF, hydrogen fluoride, because OH minus is less stable and it has a greater tendency to react with H plus and then become its conjugate acid. So the conjugate acid of hydroxide is of course water. And so what's another thing that we learn from this trend? Well, we know that when an acid is stronger, its conjugate base is weaker because the conjugate base is more stable. And if we say it the other way around, if a base is stronger, then its conjugate acid is weaker. And that's how we can compare the strength of bases as well. Now, having talked about what happens across a period, let me address what happens down a group. Because, down a group, the electronegativity of the element actually decreases. And does that mean that the acid will be weaker and weaker? Well, down a group, the really significant factor here is that the ionic radius increases and the charge density decreases. Because down the group, that your ions or your atoms will get bigger and bigger, and so the charge density, which depends on the size of the ion and also the charge itself, will actually decrease, and this will actually increase the stability of the conjugate base. So this effect is much more significant than a decrease in electronegativity of the elements down the group. Instead, down the group, the ionic radius factor kind of dominates, and the stability of the conjugate base increases. So the stability of iodide ions is much greater than the stability of fluoride ions, even though fluorine is much more electronegative than iodine. So here the significant factor is that iodide ions are much bigger than fluoride ions, and so the charge density of iodide ions is much smaller. So the acid strength actually increases down the group. And as you can see from here, Hi, the strength is greater than Hf. And that's something you should take note of. So these two trends are just really useful, and um, they can help in a lot of situations. So what if we are dealing with oxo acids? Well, in oxo acids, there is another perhaps more significant factor that you need to consider, and that is charge delocalization. So something we are very concerned with in chemistry is resonance. So these three diagrams here are called resonance structures. So although you might think that all three structures are the same, they're actually not the same. So here you have a lone pair on oxygen, this negatively charged oxygen atom here. And this lone pair is actually positioned in a p orbital. And so it can overlap with S with the orbital of sulfur and kind of become a pi bond here. But you need to keep the valency of sulfur as well. So this bond can actually move here to become a negative charge, and this negative charge actually can move here, and this bond can become a negative charge. So we know that if all four oxygen atoms are distinct from each other, then this negative charge is actually spreaded across all three oxygen atoms here. So how do we know where the negative charge is exactly? Well, we don't really know that. So let me clear this. Okay, so when we draw resonance structures, we shouldn't break or form single bonds, because those are usually your sigma bonds, and if you break those, it actually doesn't really make a lot of chemical sense, at least at this level. And we shouldn't jump atoms. So for example, you shouldn't make this bond go here. That would be like jumping atoms. So yeah, so we should always also avoid charge separation. So we shouldn't make the positive. So we shouldn't do something like this. So for example, we shouldn't do something like this. Then if you remove this bond, you get a negative charge here. So if you remove this bond, you get a positive charge here. You get a negative charge here, then this is considered charge separation, because here you have two negative charges, they have a positive charge right next to them, and it doesn't really make sense. So the resonance structure is really less stable than compared to any of the three resonance structures shown here. I haven't talked about how to draw resonance structures. Let me just address the question real quick. So how do we know where exactly is the negative charge? Well, the negative charge is actually said to be delocalized across all three oxygen atoms, and that causes stabilization because each oxygen atom needs to bear a smaller negative charge. So that is called charge delocalization. So instead of being localized at one of the oxygens, the charge is actually spread across all three, and that makes the anion here more stable. So if you consider the HSO4 minus ion, which is the ion that you get right after you deprotonate H2SO4, then you have a -1 charge spread across 3 oxygens. You can draw it out for yourself to really convince yourself. Then if you HSO3 minus, you have a -1 charge spread across 2 O's. So I'm not going to draw out all 2 resonance structures. Let me just demonstrate with one resonance structure here. So HSO3, so this is HSO3 minus ion. So the minus charge is located here. So it can only the lone pair can only come here, and the bond pair can only go there. So you don't have 2 resonance structures. Similarly, for SO3 2 minus ions, you have a -2 charge spread across 2 oxygens. So the conclusion would be that HSO4 minus is the most stable out of these 3, followed by HSO3 minus, then SO3 2 minus. This is because your so-called charge density, or the charge each oxygen has to bear, actually increases across actually increases from HSO4 to HSO3 minus to SO4 2 minus. So the acid strength of H2SO4 is actually greater than H2SO3, and then that is greater than NaHSO3. So something that we can learn from this is that when you deprotonate an acid, a polyprotic acid, so for example, you deprotonate H3PO4, your phosphoric acid, it actually H3PO4 is actually stronger than H2PO4 minus, and that is stronger than HPO4 2 minus, which is in turn stronger than PO4 3 minus. So when you deprotonate an acid, the acid strength actually decreases for each of the subsequent species. So an empirical rule that scientists have found is that the pKa of an oxo acid is approximately 8 minus 5 times the number of double O bonds. So for example, you have your H2SO4, and in H2SO4, the number of double O bonds is actually 2, and because of that, the pKa will be approximately -2, and that's quite close to the empirical value. And because of this rule, we know that the pKa increases by approximately 5 units with each H class dissociation. So that means when if your pKa for H2SO4 is -2, then the pKa of HSO4 minus is approximately -2 plus 5, and that's 3. And when you deprotonate it even more, then its pKa increases even more. And another thing that we get from this rule is that the central atom doesn't really affect the acid strength significantly. For example, when you compare H2SO4 with HNO3, the pKa's of them are both quite similar and around -2. So it works in that case. However, it doesn't work in all the cases, and so you still need theoretical data. You still need experimental data to back you up. Now let me talk about the last, actually not last method, but another method of comparing the stability of conjugate bases. So other than comparing the charge delocalization, for example, in the carboxylate group, so the negative charge is actually spread across 2 oxygen atoms. We can also consider the inductive effects. So what is inductive effect? Well, electronegative atoms such as fluorine, chlorine, oxygen, and nitrogen actually pull electron density away from the basic site. And that is the COO minus group in carboxylates, and that will help stabilize the negative charge. Meanwhile, on the other hand, alkyl group such as carbon chains donate electron density, and that would destabilize the negative charge because you intensify the negative charge on the basic sites. So A thing to note here is that the length or the shape of the alcohol, the length or the shape of the alcohol group itself doesn't really affect how much electron density they donate. Rather, this depends on how many alkyl groups are around the basic site, because of course inductive effects will decrease over distance. Yeah, so inductive effect diminishes with distance. So if you have an electronegative atom that is right next to the basic site, that then its effect in stabilizing the anion is much greater than an electronegative atom that is a few carbons away from the basic site. And another thing to note here is that alkyl groups are really weakly donating. So if you have a fluorine that's right next to the basic site, the effect is probably going to wing out over the electron donation by the alkyl groups that's next to it. And as a rule of thumb, the smaller the charge density at the basic site in the conjugate base, the more stabilized or the weaker will be the base, and the stronger will the acid be. So let me now address aqua ions. So the thing that we use to compare the acidity is the charge density. So a smaller aqua ion be high will be more highly charged. So sorry, let me correct that. A smaller aqua ion with a higher charge will have a higher charge density, and that will give rise to a greater acidity. So this is because a higher charge density um on the of the ion will cause it to distort the electron cloud of water ligands that surround it more, and that weakens the OH bond in the water ligands further and causes the H plus to be dissociated more easily. So, for example, sodium's aqua ion is more acidic than potassium's because sodium ion is smaller than potassium ions, even though they have the same charge. A really important thing that we must take note of is the D block and later P block ions are more acidic than S block ions. So the reason for this is the significant covalent character in bonding between the metal ion and water ligand actually help the the negative charge after dissociation to better delocalize. So after you dissociate a H plus from water, you get OH minus, and the minus charge on the oxygen actually can better delocalize into the system of the aqua ion, and that will help stabilize the resulting conjugate base. So for example, copper 2's aqua ion is more acidic than magnesium's aqua ion because copper 2 is in D block while magnesium is in S block. And that's all for the BL acid and base theory. And now we're going to move on to something slightly more complicated, and that's a Lewis acid base theory. So instead of basing the theory on the transfer of H plus ions, which I'm sure you're more familiar with, here we are basing the acid-base reactions based on the transfer of electron pairs. So an acid is an electron acceptor while a base is an electron donor in the Lewis definition. So this theory, instead of concerning ourselves only about H plus ions, we concern ourselves about all types of ions, and that's a broader definition than the BL acid-base theory. So let me now introduce some very common Lewis acid-base reactions. And the first is adduct formation and dissociation. So for example, you have your BF3 and NH3. When they react together to form an adduct, so there's a bond between B and N in this case. So BF3 is the acid because it accepts a lone pair from NH3. So here the NH3 actually, the lone pair N actually datively bonds to C. So here, one thing that we like to draw is here we have BF3. And we have our NH3. So NH3 is here. And a lone pair on N actually datively bonds to B. So here B only has 6 electrons around it, and that's why it's electron deficient. So it can act as a Lewis acid and accept electrons from nitrogen, and because of that, a bond actually forms between N and B. So instead of only existing here as a lone pair, the lone pair becomes a bond pair. And another way that we can actually show this instead of drawing an arrow is actually we draw a bond here, and the N here we give it a formal positive charge. For the B here, we give it a formal negative charge. So does the formal charge mean? Well, N used used to have 5 electrons around it, and now it has it has 1, 2, 3, and 4. So assuming that we break all the bonds homolytically, or each of the bond pair actually goes to the atom right next to it, sorry, each electron in a bond pair goes to the atom that's next to it. Then we count how many electrons does the atom have now. So it has 1, 2, 3, and 4 electrons for nitrogen, and it used to have 5 before this dative bond formed. So the formal charge of this nitrogen is plus, because it used to have 5 electrons, now it has 4. So it's a plus charge. Then for B here, before this bond forms, it has 1, 2, 3 electrons, but now you have one more here from the bond pair, and that's why it has a formal negative charge. So that's just an introduction to representing formal charges, and that will come into play in organic chemistry more often, but it's good to bear it in mind. So returning to inorganic chemistry, an example of adduct dissociation is actually the thermal decomposition of calcium carbonate. So for calcium carbonate, it actually breaks down into calcium oxide as well as carbon dioxide. So here, the O2 minus ion, oxide ion, is actually considered a base, while the CO2 um, or, or carbon dioxide is considered the acid. So how does this work? Let me just use a really simplified representation. So here you have an O2 minus ion, and it has many, many lone pairs, okay? And then you have your CO2. So that's your carbon dioxide, and this lone pair can datively bond to this carbon. And if this bond pair goes to become a lone pair on oxygen, then we will have our CO3 2 minus ion. So yeah, so when this decomposes back to its original acid and base, then it's called an adduct dissociation. So yeah, this is an example of adduct dissociation. Another type of Lewis acid-base reactions is displacement reactions. So it can be single displacement, for example, ligand substitution, or you can have your traditional acid and base reactions. So for example, for ligand substitution, your copper's aqua ion, so copper's ion with water can be the water ligands can actually be displaced by chloride ligands when you have an excess of chloride present in your solution, and then you form your CuCl4 2 minus, and that's your ligand substitution reaction, and for your Bronsted acid base reactions. You can have like H plus Cl minus gives you HCl, and the reverse reaction of that as well. So these all fall under Lewis acid-base reactions as well and fall under displacement. Then for double displacement, you can have adapt partner exchanges or dissolution of salts. So for example, you can have your Al2S3 plus 3H2O, then they actually swap partners. So H plus, instead of being paired with OH minus, the OH minus goes to the Al and kicks out the S. So the S will then partner with the H plus, and so that's considered a displacement reaction because here we can view the OH minus as donating its lone pair to Al3 plus, and we can view the S2 minus as donating its lone pair to H plus, and that's an acid-base reaction under the Lewis definition. And for NaCl's dissolution, it actually, so instead of Na paired with Cl, you pair Na plus with water and you pair Cl minus with water. So yeah, so the acids will then be Na plus and H2O, and the bases will be Cl minus and H2O. So your acids are your electron acceptors, while your bases are your electron donors. So yeah, an easier way to view this is just the Na plus swaps place with the H plus in water. Under the Lewis definition, we can also compare acid and base strength. So for Bl acids, we measure the base strength. For Bl bases, we measure the base strength based on how strongly they bind to H plus, and acid strength based on the degree of H plus dissociation. So under the Bl theory, it's very clear cut. Our benchmark is H plus, but there's no benchmark in acid and bases in Lewis theory because you can't really like benchmark electron donation in a simple sense. Like it's easier to benchmark using H plus than using electrons. So actually, in Lewis theory, the choice of acid actually affects the ability of base to bind to it because a lot of things affect the affinity, the electron affinity, or the willingness of a species to donate or accept electrons. So there is really no benchmark in Lewis theory. So we can't really define an acid as absolutely stronger than another. In fact, we need to look at what is the target base that you are comparing the relative acid strength against. So relatively, strength are affected by inductive and resonance effect, which I have covered before, and I will address more in the next slide, and also steric effects. So steric effects is when you have bulky groups. For example, you have your C bracket CH3 bracket 3 groups. So you have your butyl groups, and these kind of groups might cause repulsion and strain because there's no electron clouds repel each other sometimes. So they might cause repulsion and strain, and that makes acid-base reactions unfavorable because the acid and base cannot approach each other very easily, and even after they approach, the molecule is highly unstable because there is some kind of strain inside the molecule, and the molecule wants to fall apart and dissociate back into its acid and base. So now I'm going to elaborate more on inductive effects and resonance. So inductive effect is what we call the sigma effect. So for alkyl groups, they are electron donating because of something called hyperconjugation, and it actually increases the charge density around, like it donates electron density towards other parts of the molecule. So I'm not going to go into the technicalities of that, but it is something that you can read up on if you're interested. And for electron negative elements, they are electron withdrawing, and they will decrease the charge density of the other parts of the molecule. However, inductive effects actually diminishes very significantly over distance. So usually when the electronegative atom is like two carbons away from our sort, like the sites that we are observing or we're concerned about, we actually don't really care about atoms that are that far away. So a higher charge density on the atom bearing the lone pair or bearing the negative charge will actually result in a stronger base or a base that is less stable. So the acid or the conjugate acid of that be um will be less acidic. As I mentioned in the Bronsted theory, but here because we don't really have conjugate acid base pairs anymore, we actually are concerned about how strong the base is. So if you have a higher charge density, then the base is stronger and less stable. So it will have a greater tendency to react with a Lewis acid. Then we have our resonance effect, which we call the pi effect. So it acts along pi bonds. So for inductive, it acts along sigma bonds. So because that's something that just goes along the sigma bonds, while for resonance, you are dealing with delocalization, you're dealing with resonance structures, which is commonly associated with pi bonds. So you can refer to slide 8 for how to draw resonance structures. And just to explain this in the context of Lewis theory, let me give an example. So, for example, why BF3 is a weaker acid than BCl3 is because for both BF3 and BCl3 you can draw these resonance structures. However, the p orbitals of B and halogen atoms overlap better in BF3 than BCl3 because B and F are in the same period, so their orbital sizes are similar, while BCl3, B and Cl are in different periods, so Cl orbitals, electron orbitals are much bigger than B electron orbitals, so they don't overlap as well. And that is why for BF3, it actually all these four resonance structures contribute significantly to how the electrons are how they are delocalized or distributed. But for BCl3, these three resonance structures are not that significant because the delocalization because the overlap of the orbitals are poorer. So for BCl3, it mostly the resonance structure that contributes the most significantly compared to BF3 is actually this first structure. So here the halogen atom donates more electron density to B in BF3 through the resonance effect, and BF3 will be less electron deficient and a weaker acid. So it's less likely to accept lone pair of electrons from a Lewis base. So this might be contradictory to what we might deduce based on inductive effects because F is more electronegative than Cl, so we would expect F to pull more electron density away from B, making it more electron deficient. However, that is not the case because here the resonance effect is stronger. So in chemistry, there are often opposing effects that you need to consider, and one can be stronger than the other in some cases, while the reverse is true in other cases. So, ultimately, you should consider the experimental data as well as other factors. So, the last thing that I'm going to address here is the hard soft acid base classification. So, the HSAB principle actually helps us predict the favorability of reactions based on the polarizability of ions. So this whole classification is based on polarizability. So what does polarizability mean? Well, in HSAB terms, when you have lower polarizability, your acid or base will be harder and vice versa. So a larger ion with a lower charge will correspond to a softer or more polarizable kind of ion because your electron cloud is larger, and it's less likely to it's more likely to be polarized, like it's more likely to be distorted and pulled by other ions, so that's softer. So acid and base, for acid and base reactions between hard acid and hard base, or between soft acid and soft base, are usually preferred over reactions where one is hard and one is soft. So acid and base that are like each other in terms of polarizability actually react more favorability, not more favorably than in other cases. However, this is not a hard and fast rule, so you should always consider other factors as well. So when you have both the acid and base are hard, then the interactions between them are highly ionic. While if both are soft, then the interactions between them are highly covalent. So remember that for HSAB, the principle doesn't really say anything about the strength of the bond. Whether something is formed depends on both the bond strength and other stabilization factors, HSAB being one of them. So we are talking about very different things here. So the strength of a bond and the polarizability of ions and how much the ions kind of like each other are are not the same thing. So you shouldn't confuse between them. And HSAB only talks about how much the interaction is favored in terms of polarizability and not strength. So here I have placed two tables here, and these tables introduce you to some examples of hard acid, soft acid, hard bases, and soft bases. As you can see, the polarizability is affected by the ionic radius and charge. So the higher the charge, the lower the polarizability, the higher the ionic radius, the higher the polarizability. So here the borderline acid and bases just mean they're kind of like in between, and it will really depend on a lot of other factors. So HSAB isn't usually the significant factors at play for borderline acids and bases and how they react with each other. As for hard acids and soft acids, remember that we are just placing them into categories, and these categories might not work all the time, but usually they work. So the hard acids actually like the hard bases, or the soft acids like the soft bases. So when do we use HSAB? I know I talked about a lot of things here, and it might get really confusing. So we use it when we're comparing similar species. So for example, if we want to know whether F minus or I minus bind better with Ag plus. So here we're considering two halides and comparing between them. So we can compare between them. But or we can compare between BF3 or AlCl3, and which one of them binds better to NH3. So here both have similar structures. Both the B and Al have three bonds to a halogen atom, and both of them have 6 electrons surrounding them. So the electronic structures of these two are similar, and that's why we can compare between them. But we can't use HSAB when we are trying to determine whether H plus or BF3 binds better with OH minus, because H plus and BF3 are both very different from each other in the way they bind, as well as their electronic structure, as well as they're just very different, and we shouldn't compare between them using HSAB. And another thing we need to take note is when we're using HSAB, the compared acid and bases shouldn't have drastically different strength. So here's again, strength is not the same as hardness or polarizability. So please do not confuse between these two. They're completely different they're completely different ways that we are describing our acid and bases, and they might have opposing effects, and when they have opposing effects, we need to consider which one is more significant, and we shouldn't confuse between them by trying to explain one using the other. So, for example, sometimes the strength of the bonds dominates whether a reaction is feasible. So, for example, compare H plus with Na plus, when you are even though they might both be hard, they they're just very different from each other because they form bonds very differently. Na plus forms a lot of for example, when you consider NaCl and HCl, um, or you consider a lot of those, because using HSAB you can't really compare between these two. Both are very both Na plus and H plus are hard and Cl minus is soft, and you can't really compare. Or you can't really compare HS with NAF and tell me which one will be formed using just HSAB, because it doesn't really make sense for you to compare two things that are really different. So H plus and Na plus, they're not in the same group. Their chemical properties are pretty different, and that's why you shouldn't try to use HSAB to determine which one will react more favorably with F minus or Cl minus or other Lewis bases, because it doesn't really work that way. And you should only use HSAB when you have a benchmark. So when you're comparing which Lewis acid will bind more favorably with a Lewis base, you need to have a predetermined Lewis base in mind. So you cannot compare between the reaction of H plus and Cl minus with the reaction between, let's say, Na plus and F minus, because it doesn't really make sense. You don't have a benchmark Lewis base to compare H plus and Na plus with, so you cannot just compare the favorability of two reactions that are completely different with no benchmark. So what we should do instead is, for example, to compare a hard acid and a soft acid against the same base and determine which one will interact more favorably. And remember, HSAB has exceptions. It's not a hard and fast rule, and you should consider other factors. So it is just one of the many, many factors that we are considering for Lewis acid and bases, and we shouldn't apply it blindly all the time. We should also consider bond strength, consider what solvent the reaction is carried out in, consider a lot of different things like the state symbols of each of the ions, the acids and bases. There are just a lot of things they need to figure out, and I guess the best way to do that is just to do more questions, see more compounds, and then you will have a general sense of when to apply HSAB, when to apply bond strength, when to apply Lewis acid base theory even, and that will really help you in the long run. So I have kind of gathered several questions here that really helped me when I was studying for this topic. And I have put a link in the description of this video where you can access this set of slides and you can try out these questions. And if you want your answers checked, feel free to leave your question number and answer in the comments, and we can start a discussion from there. Finally, if you are interested in what actually underlies the HSAB principle, if you're curious about the molecular orbital theory behind, you can actually access this link here to that will lead you to a page on Chemistry LibreText that explains this in much greater detail. And with this, I have come to the end of my slides, and thank you so much for watching, and feel free to clarify or discuss anything in the comments or reach out to me in the comments. Thank you.